A perfect hexagon swirls at Saturn's North Pole, a geometric storm wider than our entire planet. We are journeying to uncover 25 of Saturn's most profound and unresolved secrets. By the end, you will grasp why this ringed world remains one of our solar system's greatest puzzles. We will confront a moon that rains water into space and investigate rings that are actively vanishing before our eyes. Which of Saturn's enigmas do you believe holds the key to understanding our cosmic neighborhood? This immense six-sided hurricane is a feature that simply should not exist. It is a geometric whirlwind of clouds, a perfect hexagon etched into Saturn's North Pole that has remained locked in place for at least 4 decades, far outlasting any storm on Earth. Its sides are each longer than the diameter of our entire planet, making it a structure of almost unimaginable scale. The precision of its shape is what baffles scientists the most. On a rotating sphere of gas, we expect to see swirling vortices and ovals, not sharp-angled, persistent polygons. How does nature carve and maintain such a perfect form in a chaotic, turbulent atmosphere? The leading theories point to the complex dance of fluids and gases. One idea suggests that a steep latitudinal gradient in the speed of Saturn's jet streams could create a phenomenon where atmospheric waves become trapped, shaping the flow into this hexagonal pattern. It is like a very specific planet-sized vibration in the air, a standing wave that organizes the chaos around it. Another explanation delves into complex fluid dynamics, proposing that deep, rotating columns of air act like a hidden mold, shaping the clouds above into this six-sided figure. Yet no single theory has managed to fully solve the puzzle. Each computer model can replicate parts of the hexagon, but none have perfectly captured its long-term stability and stark geometric perfection. This leaves us with a fundamental question about the very nature of planetary atmospheres. Is Saturn's hexagon a rare celestial coincidence, or is it a sign of fluid physics we have yet to fully understand? From the polar hexagon, we shift our gaze to the planet's magnificent rings, where another fleeting mystery dances in and out of view. Across the vast, flat expanse of the B ring, strange radial features known as spokes suddenly materialize. They look like ghostly brushstrokes on a cosmic canvas, immense dark or bright streaks that can stretch for thousands of miles. Unlike the countless ring particles locked in their orderly orbits, these spokes appear, rotate, and vanish over just a few hours. Their transient nature makes them incredibly difficult to study, a celestial apparition that challenges our understanding of this dynamic system. The leading suspect in their formation is Saturn's powerful magnetic field. Scientists theorize that tiny micron-sized dust particles high above the ring plane can become electrically charged. This charge, interacting with the planet's magnetosphere, might cause these fine particles to levitate, lifting them up and out of the ring layer. This creates the appearance of a dark or bright spoke against the brighter, icy background of the rings, but the precise trigger for this event remains elusive. Is it caused by meteoroid impacts kicking up dust or by powerful electrostatic discharges, or is it a more complex seasonal phenomenon as Saturn's tilt changes the angle of sunlight on the rings? Decades after their initial discovery, these enigmatic features continue to appear, a silent, rotating ballet of dust and electricity that we are only just beginning to comprehend. This very spectacle of the rings, those ghostly spokes and all, leads us directly to one of astronomy's oldest and most profound questions. Where did Saturn's rings even come from? Their breathtaking beauty masks a violent and uncertain past. For centuries, we assumed the rings were as ancient as the planet itself, a primordial relic from the birth of the solar system. The leading theory for a long time suggested that a moon, perhaps as large as the planet Mercury, strayed too close to Saturn. The planet's immense gravity would have torn this unfortunate world apart, shattering it into countless fragments. A catastrophic collision could have done the same, with a massive comet or asteroid striking a moon and pulverizing it. The resulting debris, caught in Saturn's gravitational sway, would have then slowly flattened into the disk of rings we see today. It is a dramatic and compelling story of celestial destruction, yet other ideas challenge this notion of a violent birth. Another hypothesis proposes that the rings are simply leftover building blocks, the remnants of the protoplanetary disk of gas and dust that Saturn itself formed from. In this view, the material never managed to coalesce into a moon at all. instead being held in a delicate balance, forever destined to orbit as a fragmented halo. But then came data that turned everything on its head. Measurements from the Cassini spacecraft revealed that the rings are remarkably clean and bright, composed almost entirely of pure water ice. If they were truly billions of years old, they should have been darkened and polluted by constant bombardment from cosmic dust. This startling evidence points to a far more recent origin. The rings we find so iconic might be a mere temporary decoration, perhaps only 100 million years old, a fleeting feature in the long life of a 4.5 billion-year-old planet. This raises an almost philosophical dilemma. Were the rings born from the epic destruction of a lost moon, or are they the pristine, youthful remains of a passing comet that was captured and torn apart? We are left gazing at a structure that might not have existed when dinosaurs walked the Earth, a beautiful, transient mystery that frames the gas giant. This beautiful and transient ring system is actively vanishing before our eyes. Saturn is losing its rings at a rate that is staggering, a phenomenon astronomers have poetically named ring rain. High above the planet's equator, tiny particles of ice from the inner rings are feeling a subtle but relentless pull. They are becoming electrically charged by sunlight and by plasma clouds from Saturn's magnetosphere. This charge allows the planet's own gravity to draw them in, guiding them along invisible magnetic field lines like water droplets sliding down a window pane. These icy fragments, some no larger than a dust mote, streak into the upper atmosphere at tremendous speeds. As they fall, they vaporize, creating a steady drizzle of water and other compounds into the gas giant. This is not a gentle shower but a torrential downpour on a planetary scale. Estimates suggest this rain drains an amount of water equivalent to an Olympic-sized swimming pool from the rings every single day. At this rate, the entire ring system could be gone in just 100 million years. For a planet over 4 billion years old, that is the blink of a cosmic eye. This discovery forces us to see Saturn's rings not as a permanent fixture, but as a youthful and fleeting spectacle. We are witnessing a dynamic, evolving system in its final, glorious chapter. The rings are not just a static picture, they are a process, a cascade of material with a definite expiration date. What does this mean for their very existence? It suggests that we are living in a uniquely privileged moment in the solar system's history, a narrow window of time to behold one of its most magnificent sights. That same rain of particles vanishing from the rings may hold the key to another of Saturn's riddles, one that orbits 1 million miles away. Iapetus is a moon of two faces, a celestial yin and yang. One of its hemispheres is as bright and reflective as fresh snow, while the other is stained a deep, dark reddish brown, as dark as freshly poured asphalt. This stark division is so precise it looks as though the moon was meticulously painted. For centuries, astronomers struggled to explain how such a dramatic contrast could exist. The prevailing theory points an accusatory finger outward, toward the distant, dark moon Phoebe. Phoebe orbits in the opposite direction to Iapetus and many of Saturn's other moons, and it is constantly bombarded by tiny impacts. These collisions kick up a fine, dark dust which slowly spirals inward toward Saturn. As Iapetus plows through this vast, faint ring of debris, the dust preferentially strikes its leading face, the hemisphere that is always pointed forward in its orbit. Like a windshield collecting bugs on a highway, that one side gets coated, but this is only half the story. Once the dark material settles, a powerful feedback loop begins. The darkened areas absorb more sunlight, growing warmer. This causes any exposed water ice on that side to sublimate, turning directly from a solid into a gas. This water vapor then drifts across the moon and refreezes onto the colder, brighter trailing hemisphere and the poles, further brightening those regions and deepening the darkness of the other. It is a self-reinforcing process of thermal segregation that has created one of the most striking visual dichotomies in our solar system. Yet just as we begin to understand its two-toned face, Iapetus reveals another, even stranger feature. Stretching along its equator is a bizarre mountain ridge that runs for over 800 miles, encircling the entire moon. In some places, this ridge towers over 8 miles high, making it one of the most dramatic and perplexing landscapes ever seen. How did such a perfect equatorial wall form? Some scientists suggest it could be the frozen remains of a ring system that Iapetus once had, material that collapsed down onto the surface. Others propose it is a relic from a time when the moon spun much faster and its crust buckled along the equator, or perhaps it was formed by material welling up from the moon's interior. This combination of a two-faced world and a colossal equatorial belt makes Iapetus a unique geological puzzle, a moon that challenges our understanding of how worlds are born and evolve. Far from the darkened face of Iapetus, a small icy moon is actively broadcasting its secrets into the void. Enceladus, a world barely 300 miles across, should be a frozen, geologically dead relic. Instead, its south pole is a scene of spectacular activity. Gigantic plumes of water vapor and ice crystals erupt from deep fissures known as tiger stripes, shooting hundreds of miles into space. These are not random geysers, but a continuous, powerful outpouring from a hidden sea. The Cassini spacecraft flew right through these plumes, tasting their composition, and the results were nothing short of revolutionary. The analysis confirmed that these jets are not just water. They contain a fascinating cocktail of simple organic molecules, the chemical building blocks essential for life as we know it. But the most critical ingredient was salt. The ice grains were rich in sodium chloride, common table salt, a telltale sign that the water has been in contact with a rocky ocean floor. This single piece of evidence transformed our understanding. Enceladus is not just a frozen ball of ice. It harbors a global subsurface ocean, a vast body of liquid water trapped between its icy crust and its rocky core. This shifts the entire conversation about this tiny moon. We are no longer looking at a simple icy satellite. We are looking at a world with all the fundamental ingredients for habitability. Liquid water, a source of chemical energy from hydrothermal vents on the seafloor, and the organic compounds needed for biochemistry. This trifecta makes Enceladus one of the most promising places in our entire solar system to search for life beyond Earth. Could there be something swimming in those dark, sunless waters? We do not know, but this small, active moon has forcefully declared that the search for life is no longer confined to planets within a star's habitable zone. It can thrive in the most unexpected places, warmed not by sunlight, but by the gravitational flexing of a giant planet. This same gravitational force that sculpts the geysers of Enceladus has twisted another of Saturn's moons into a form of pure chaos. Hyperion is a world that defies every expectation, a celestial sponge frozen in time. Its surface is a nightmarish landscape of deep, dark pits and jagged ridges, a porous honeycomb of craters within craters. Nothing about this moon is normal. It tumbles to its orbit in a completely unpredictable, chaotic rotation, never presenting the same face to Saturn twice in a row. One moment its north pole is facing the planet, the next it is spinning end over end, a dizzying wobble governed by the gravitational pushes and pulls from Titan and its other siblings. This erratic motion means that its surface is baked by sunlight from every possible angle, preventing any consistent weather patterns or seasons from forming. Its incredibly low density tells us that it is not a solid ball of rock and ice. Instead, Hyperion is mostly empty space, a rubble pile with a porosity of over 40%. You could almost crush it in your hands if it were not 270 miles across. The leading theory for its bizarre texture is a perfect storm of cosmic conditions. In an environment with extremely low gravity, impacts do not create neat, bowl-shaped craters. When a comet or asteroid strikes Hyperion, the shockwave travels through its fragile, porous body. Instead of blasting material out in a classic crater formation, the impact compresses the weak surface, much like pressing your thumb into a soft loaf of bread. The material is not ejected into space, but simply compacted downward and inward, leaving behind these deep, sharp-edged pits. Over billions of years, this process has repeated countless times, with new impacts eroding the walls of old craters, sculpting this cosmic pumicestone. Yet this explanation only deepens the mystery. Why is Hyperion the only object we know of that looks like this? Other low-density moons and asteroids exist, but none display such an extreme, sponge-like texture. Was it the victim of a uniquely violent history, or does its peculiar composition make it exceptionally susceptible to this kind of erosion? This tumbling, porous world stands as a stark reminder that even in a single planetary system, nature can produce forms of bewildering and unique strangeness. While Hyperion tumbles in chaotic darkness, another of Saturn's moons basks in a hazy, golden glow, harboring a landscape hauntingly familiar. Titan is a world with rivers, lakes, and rolling hills, yet it is utterly alien. Here the hydrologic cycle runs on liquid methane instead of water. This is a place where it rains gasoline, where rivers of liquefied natural gas carve valleys, and where great seas of hydrocarbons lap against icy shores. It is the only other world in our solar system with a stable liquid on its surface, a distorted mirror of our own planet's active geology, but this entire system is built on a foundation of mystery. Sunlight constantly breaks apart methane molecules in Titan's thick atmosphere, a process that should have depleted all the surface liquid in a mere blink of geological time, perhaps just a few tens of millions of years. Given that Titan is billions of years old, its abundant methane seas present a profound enigma. Where does it all come from? How is this Earth-like cycle continuously replenished? Some scientists look deep below the icy crust, proposing a vast subsurface reservoir of liquid methane and ethane, a global aquifer that slowly seeps to the surface to feed the lakes and rivers. This hidden ocean could act as a giant buffer, releasing fresh methane to stabilize the atmosphere. Others suggest the methane might be of geological origin, released from the interior through cryoval, canals that spew cold slush of water, ammonia and methane instead of molten rock. These icy eruptions would act like a planetary supply line, regularly injecting new methane into the system to counter the destruction happening high above. Yet finding definitive evidence for these theoretical resupply mechanisms has proven incredibly difficult. The Cassini mission mapped vast polar seas like Kraken Mare, but it could not peer deep enough to confirm the subterranean reservoir. It glimpsed potential cryovolcanic features, but none that unequivocally prove they are active today. This leaves us with a world that should not look the way it does. We see a dynamic, evolving landscape driven by rain and rivers, a clear sign of an active climate, but the fuel for that entire engine remains hidden from view. Titan's very existence as an Earth-like world challenges our understanding of planetary chemistry and geology, forcing us to ask what other strange, liquid-based cycles might exist on worlds far beyond our own. Even the planet's fundamental heartbeat, its rotation, defies simple measurement. Determining the length of a Saturnian day has proven to be a surprisingly complex puzzle, one that reveals just how little we understand about the giant's hidden interior. Unlike a rocky world like Earth, where we can time the spin of a solid surface, a gas giant has no fixed ground to track. For decades, scientists relied on two main methods. They would clock the movement of prominent atmospheric features, those swirling clouds and storms, or they would listen for the rhythmic pulse of the planet's radio emissions, which are tied to its magnetic field. With Jupiter, these two methods gave roughly the same answer, but with Saturn, they produced wildly different results. Tracking the clouds suggested a day lasting about 10 hours and 33 minutes. But when the Voyager probes measured the magnetic field's wobble, it indicated a day of 10 hours and 40 minutes. A difference of just 7 minutes might not seem like much, but for planetary scientists, it was a massive discrepancy. This inconsistency points to a deep and fundamental mystery. Saturn's magnetic field is almost perfectly aligned with its axis of rotation, a unique trait in our solar system. This perfect alignment means the field does not wobble noticeably as the planet spins, making its rotation period incredibly difficult to detect from the magnetic signals alone. It is like trying to find the center of a perfectly symmetrical spinning top. This forces us to ask what is really happening deep within the planet. The visible clouds we track are just the outermost layer of a vast, churning fluid atmosphere, and they can be blown by winds, speeding up or slowing down relative to the planet's true internal spin. The true rotation rate must come from the solid core, buried tens of thousands of miles beneath the clouds, so which measurement, if any, reflects that hidden heartbeat. The confusion suggests that our basic models of gas giant interiors are incomplete. There might be a complex interaction between the deep, rotating core and the outer layers of metallic hydrogen that generate the magnetic field, creating a disconnect between the interior spin and the field we observe. Unlocking Saturn's true rotation is not just about setting a clock, It is about deciphering the very structure and dynamics of a world that has no surface. Deep beneath the swirling cloud tops, another kind of storm unleashes a power almost beyond comprehension. Saturn is home to lightning strikes of unimaginable ferocity, electrical discharges that dwarf anything we experience on Earth. A single bolt from one of these superstorms can be thousands of times more energetic than its terrestrial counterpart, releasing more power than the entire world uses in a year. These are not the brief, localized flashes of a summer thunderstorm. They are continent-sized eruptions of raw energy, flickering deep within the planet's turbulent weather layers. For decades, we could not see this lightning directly, hidden as it is by a thick upper haze of ammonia ice. Instead, we listened. Spacecraft like Voyager and Cassini detected their unmistakable signature, a sharp, crackling burst of static across the radio spectrum. Scientists named these signals Saturn electrostatic discharges, and they revealed a world crackling with electrical violence. The mystery lies in the engine that drives such colossal displays. On Earth, lightning is fueled by the upward movement of warm, moist air and the collision of ice crystals within clouds. But Saturn's atmosphere is profoundly alien, composed mostly of hydrogen and helium with traces of water and ammonia. The mechanism that separates electrical charge on such a massive scale, creating voltages high enough to arc across hundreds of miles of thick atmosphere, remains poorly understood. Is it driven by a colossal friction between ammonia and water ice crystals churning in unimaginable updrafts, or does the immense pressure and unique chemistry at deeper atmospheric levels, where water may form slushy clouds, generate charge in a way we have never witnessed? The sporadic nature of these storms adds another layer of intrigue. They can rage for months, unleashing multiple strikes per second, and then fall silent for years. What atmospheric upheaval suddenly flips the switch on this planetary scale generator? These radio whispers from the clouds are a stark reminder that the forces shaping this gas giant are not just vast, they are electrically alive. The same electrical storms that crackle within Saturn's clouds are dwarfed by a far gentler, yet equally mysterious, phenomenon occurring within its rings. Etched into the bright bands of the ring are thousands of peculiar shapes known as propellers. From a distance, they look like tiny, twin-bladed aircraft propellers carved into the ice, each one a delicate signature of a hidden force. These are not solid objects we can see, but the gravitational footprints of unseen moonlets, tiny worlds likely no larger than a kilometer across. They are embedded within the ring material itself, and as they orbit Saturn, their weak gravity is just strong enough to clear a path. They cannot open a full gap like the moonpan does in the Enceladus division, but they can push the surrounding ice particles aside, creating a central partial void that is flanked by two brighter, disturbed regions. This combination of a central gap and two enhanced wings of material is what gives the propeller its distinctive shape. The existence of these features tells us that the rings are not a uniform sea of ice. They are a dynamic construction site filled with countless unseen building blocks. The mystery deepens when we try to count them. The Cassini spacecraft identified thousands, from small, barely visible forms to giants with unofficial names like Blériot, after the pioneering aviator. But their exact population remains unknown. Are there tens of thousands or even millions of these tiny hidden moons? We simply do not have the resolution to see them all. Their composition is another enigma. Are they solid chunks of primordial rock and ice, the surviving kernels from which the rings themselves formed? Or are they just temporary rubble piles, loose aggregations of ring material that have managed to clump together under their own weak gravity, only to be torn apart again by Saturn's tidal forces? This leads to the greatest question of all, their origin. Are the propellers the leftover building blocks of a moon that never was, showing us the very process of planetary formation in miniature? Or are they the shattered remains of a larger moon that was destroyed, their fragments now quietly orbiting within the debris? These tiny, unseen moonlets and the ghostly shapes they carve are a silent, ongoing experiment in gravity, a hidden population that challenges our understanding of how rings and perhaps even planets are born and evolve. Another moon presents a face divided against itself. Dione, a world of water, ice, and rock, shows two dramatically different sides to the cosmos. Its trailing hemisphere, the face that looks backward as it orbits Saturn, is heavily cratered and dark, a testament to an ancient, battered surface. But turn to its leading face, the side that perpetually plows forward, and you find a world transformed. Here, the darkness is slashed by brilliant, luminous features known as the wispy terrain. These are the linea, vast networks of cliffs and troughs that gleam as if the moon has been scored by gigantic, icy claws. This stark duality forces a simple question. Why does one side of this moon look so different from the other? The answer appears to lie not just on Dione, but with its active neighbor, Enceladus. We now know that Enceladus is constantly spewing fine particles of ice into space, creating Saturn's diffuse ring. As Dione journeys around the planet, its leading hemisphere acts as a cosmic dustpan, steadily accumulating a gentle snowfall of this bright, fresh material from Enceladus. This ongoing process paints over the older, darker terrain, resurfacing it with a brilliant, reflective coat. It is a celestial makeover, delivered from a million miles away. Yet the plot thickens when we consider the wispy linea themselves. These gleaming scars are not merely surface stains. They are deep tectonic fractures, evidence of a violent and active past. This suggests Dione was not always the quiet world it appears to be today. Some scientists propose it was once geologically alive, perhaps even possessing a subsurface ocean like Enceladus. In this tumultuous past, global expansion or shifting ice shelves could have cracked its surface, creating the vast cliff networks. The bright material from Enceladus then simply settled into these fresh fractures, making them dazzle against the darker background. So is Dione's two-faced nature a story of external decoration or one of internal upheaval? The truth is likely a combination of both. It is a world whose past activity carved its skin and whose present environment then painted it, leaving us with a permanent record of cosmic forces both from within and without. While Dione presents a face of quiet accumulation, Saturn's own atmosphere can erupt in a planetary fever. Roughly once every Saturnian year, equivalent to 30 Earth years, a cosmic alarm clock seems to go off deep within the planet. A brilliant churning white spot bursts forth in the northern hemisphere, a storm so immense it quickly stretches into a tempest that completely encircles the entire globe. These are the great white spots, the largest known storm systems in our solar system. Imagine a single thunderhead growing until it is wider than our entire planet, then continuing to expand until its turbulent head meets its own tail, creating a continuous, boiling band of clouds around a world 10 times the size of Earth. The sheer energy released is staggering, a planetary-scale outburst that disrupts the entire weather system for months. The mystery is not just their size, but their timing. They have appeared with a strange regularity, observed in 1876, 1933, 1960, 1990, and 2010. This predictable cycle points to a deep, internal rhythm, a seasonal or internal pressure valve that releases build-up energy in a cataclysmic outburst. But what exactly is the trigger? One compelling theory involves the atmosphere's own weight and chemistry. Saturn's upper atmosphere is mostly hydrogen and helium, but beneath this lies a deeper layer where water vapor condenses into clouds. As the planet slowly orbits the sun, its northern hemisphere spends years in a long, gradual winter. During this time, the upper atmosphere cools, becoming denser and heavier. This creates a stable layer that acts like a lid, trapping heat and warmer, lighter air from rising from the humid depths below. The pressure builds and builds until this lid is violently blown off. The warm, moist air from the lower atmosphere then rockets upward in a colossal convective plume, much like a geyser of gas exploding through the planetary crust. As this immense bubble of air reaches the cold, high altitudes, its water vapor freezes instantly into brilliant white ammonia ice crystals, creating the characteristic bright spot that gives the storm its name. The planet's rapid rotation then shears this plume, stretching the storm head into a tail that eventually wraps all the way around the world. Yet, this elegant explanation is not a perfect fit. Why does this cycle occur so precisely every 20 to 30 years? Why do some storms appear slightly off schedule or with varying intensities? The engine driving this planetary heartbeat remains hidden, a fundamental question about the internal energy and seasonal cycles of a gas giant. We are left watching the clock, waiting for the next great outburst to see if it will finally reveal the secrets churning in Saturn's deep, hidden heart. The planetary fever of Saturn's great storms gives way to the quieter, more subtle mysteries of its moons. One such puzzle unfolded around Rhe, Saturn's second largest moon, with a discovery that turned out to be an illusion. In 2008, data from the Cassini spacecraft hinted at something unprecedented. The instruments detected a sharp, symmetrical drop in the electrons that normally stream from Saturn's magnetosphere, a dip that occurred just before and just after the spacecraft flew past Rhe. This pattern was the classic signature of solid material orbiting the moon, a ring system absorbing those particles. The announcement was electrifying. If true, Rhe would be the first moon ever discovered to have its own rings. The idea was not entirely far-fetched. Rhe is large enough that its gravity could, in theory, hold onto a disk of debris, perhaps from a long-ago impact that kicked material into orbit. We began to picture a miniature version of Saturn itself, a moon adorned with its own cosmic jewelry, but science demands verification, and so the hunt began. Subsequent Cassini passes were dedicated to a direct search. Scientists aimed the spacecraft's powerful cameras, looking for any glint of sunlight reflecting off icy ring particles. They searched for the subtle darkening of background stars as the hypothetical rings passed in front of them. They scrutinized the data for any other trace of the telltale debris. The result was a profound and puzzling silence. They found nothing, no rings, no dust clouds, no confirming evidence of any kind. The initial tantalizing signal had vanished. So what had Cassini actually detected? The leading explanation today points not to solid rings, but to a much more ethereal phenomenon. Rhe may be surrounded by a very thin and diffuse disk, not of large ice chunks, but of extremely fine dust. Alternatively, the moon itself might be the source of the mystery. It could be that Rhe's ancient, icy surface is creating a temporary and tenuous cloud of charged particles, a kind of ethereal plasma that mimicked the absorption pattern of a ring without the ring itself. The Rhe ring illusion stands as a powerful reminder of how easily we can be misled by indirect evidence, and how the relentless pursuit of truth often leads not to a simple answer, but to a deeper, more nuanced question. We thought we had found a moon with rings, but we may have instead discovered a completely new kind of interaction between a moon and its parent planet's powerful magnetic field. Even as its great storms rage below, the upper reaches of Saturn's atmosphere hold a thermal mystery that defies all logic. High above the cloud decks, where the air is thin and sunlight is weak, the temperature soars to a blistering 800 degrees Celsius. This intense heat makes no sense. Saturn is nearly 10 times farther from the Sun than Earth is, receiving only 1% of the solar energy we do. Its upper atmosphere should be frigid, a deep freeze of negative 200 degrees or colder, yet it glows with a warmth comparable to the surface of Venus. This is not a unique problem. Jupiter exhibits a similar anomaly, but on a world dominated by a colossal hexagon and vanishing rings, it adds another layer of profound confusion. How can a planet so far from the Sun have an atmosphere that seems to be cooking from within? The leading suspect is a process known as auroral heating. At Saturn's poles, the relentless solar wind slams into the planet's powerful magnetic field, funneling charged particles down into the atmosphere and creating spectacular, permanent auroras. These celestial light shows are far more than just a beautiful display. They are a massive energy delivery system. The tremendous electrical currents generated by the auroras can create powerful winds, which then channel this energy from the poles toward the equator, effectively distributing the heat across the entire planet. It is as if a giant, invisible atmospheric conveyor belt is carrying warmth from the polar ovens to the rest of the globe. Another compelling theory points to atmospheric gravity waves. These are not the gravitational waves from merging black holes, but vast, slow-moving ripples in the air itself, generated by turbulence in the lower atmosphere. Think of them as planetary-scale vibrations, like the deep resonance you might feel from a massive bell. As these waves travel upward into the thinning air, they grow in amplitude until they eventually break, much like an ocean wave crashing on a shore. This breaking wave action transfers a tremendous amount of energy and heat into the upper atmosphere. The problem is that neither of these explanations seems to provide enough energy on its own. Current models that include both auroral heating and gravity waves still fall short of accounting for the extreme temperatures we observe. This leaves a glaring gap in our understanding. Is there another, more powerful source of energy we have not yet identified? Could the complex interplay between Saturn's internal heat, its rapid rotation, and its unique magnetic field be generating a form of atmospheric heating we cannot yet replicate? This thermal puzzle forces us to reconsider the very engines that drive the climates of gas giants, suggesting that the physics of these vast worlds is far more dynamic and mysterious than we ever imagined. This delicate gravitational balance weaves its way through the orbits of two of Saturn's most intimate moons. Janus and Epimetheus are locked in a celestial dance unlike any other, two partners sharing the same ballroom but never touching. They travel on orbital paths that are separated by a mere 30 miles, a trivial distance on the cosmic scale. At such close quarters, logic dictates they should have collided eons ago, merging into a single body or violently scattering one another into the void. Yet they perform a perfectly choreographed maneuver that defies this fate. Every 4 years, as the inner, slightly faster moon begins to catch up to its outer partner, their mutual gravitational pull takes over. Instead of a catastrophic crash, they gently swap places. The moon that was on the inside track is pulled outward, while the moon on the outside is tugged inward. They exchange orbits in a graceful, predictable swap, a gravitational tango that has likely continued for billions of years. How is such a delicate ballet possible? The secret lies in the very nature of their gravitational embrace. As they approach each other, they do not simply pull each other closer, they exchange energy and momentum. The inner moon, feeling the tug of the outer moon's gravity, slows down slightly. This loss of energy causes it to drop into a higher, slower orbit. Meanwhile, the outer moon is pulled forward by the inner moon's gravity, gaining speed and energy, which pushes it into a lower, faster orbit. They effectively kick each other onto new paths, passing like two courteous strangers in a cosmic hallway. This stable, repeating cycle is a beautiful demonstration of orbital mechanics, but its existence poses a profound question of origins. How did such a fragile system form and persist in the violent, chaotic environment of the early solar system? One compelling theory suggests they were once a single moon that was shattered by a massive impact. The resulting debris then coalesced into two distinct bodies, but they were born already entwined in this resonant lock, their orbits fine-tuned by the very event that created them. Another idea proposes there are primitive planetesimals, leftover building blocks from Saturn's formation that were gently captured into this stable configuration by the planet's growing gravity. Their dance is a fossilized record of a gentler process, a rare snapshot of how celestial bodies can find harmony amidst the chaos. This 4-year orbital swap is more than just a curiosity. It is a living experiment in stability, showing us that even in the relentless pull of gravity, there can be a rhythm, a balance, and an elegant, enduring peace. The dark material staining the face of Iapetus has a suspected source, a distant and shadowy moon orbiting in the wrong direction. Phoebe is a world of profound darkness, a captured object from the outer solar system that is one of the blackest bodies we have ever seen. This is no mere coating of dust. Phoebe is intrinsically dark, a primordial relic that may have formed in the frigid depths beyond Neptune. Its retrograde orbit, moving opposite to Saturn's rotation and the flow of its other moons, is the key to the entire mystery. As Phoebe plows against the grain, it is constantly bombarded by micrometeoroids, its surface being slowly sandblasted into a fine, reddish-black powder. This dust does not simply fall away. Instead, it is caught in a subtle but relentless gravitational tug-of-war, slowly drifting inward toward Saturn, creating a vast, invisible ring of debris that spans the entire distance from Phoebe's orbit to the realm of Iapetus. It is along this cosmic highway that Iapetus travels, its leading hemisphere acting as a giant collector for this ancient, dark rain, but the composition of this material is as mysterious as its journey. Spectral analysis reveals it is not simple carbon soot. It contains complex organic compounds, the kind of tarry, carbon-rich molecules found in the most primitive asteroids and comets. This is the stuff from which life could potentially form, a primordial sludge now painting a moon. How did this material remain so dark and complex over billions of years? Why has it not been broken down completely by solar radiation? The journey itself is fraught with peril. For the dust to travel from Phoebe to Iapetus requires millions of years, a slow spiral inward where it is exposed to the harsh environment of space. The fact that it arrives at all and in sufficient quantity to paint an entire hemisphere suggests this is a continuous process, a slow-motion conveyor belt of cosmic paint that has been operating for eons. Yet this elegant theory faces a challenge. Recent studies suggest the precise chemical fingerprint of the dark material on Iapetus does not perfectly match that of Phoebe's surface. Could there be another, even more ancient source for this cosmic stain, or does the material undergo a fundamental transformation during its epic journey, its chemistry altered by sunlight and radiation until it becomes something new? The dark side of Iapetus may be a canvas, but the paint and the painter are still not fully known. That same methane cycle creating rivers and lakes on Titan comes with a chemical puzzle of its own. The math simply does not add up. Sunlight constantly bombards the methane in Titan's thick, hazy atmosphere, breaking its molecules apart. This photochemical process should act like a cosmic factory, relentlessly producing a heavier hydrocarbon called ethane. Over the billions of years of Titan's life, this factory should have churned out a staggering amount of it. Scientists once predicted that this ethane would rain down and accumulate, creating global oceans hundreds of meters deep. They expected to find a world dominated by ethane seas, a sludge-filled landscape where methane rivers flowed into vast, sluggish ethane oceans. But when the Cassini spacecraft arrived and peered through the haze, that is not what it found. The lakes and seas, while substantial, are not global, and they are composed primarily of methane, not the predicted oceans of ethane. Even the atmosphere itself holds far less ethane than the models foretold. So where did all the ethane go? It is as if a factory was seen taking in raw materials and heard operating at full capacity, but its primary product has vanished from the warehouse. One compelling theory suggests that the ethane is not missing, it is simply hiding. It may have seeped down through Titan's porous, icy crust, accumulating in a massive subterranean reservoir. This hidden ocean of liquid ethane, mixed with water and ammonia, could lie deep beneath the surface, acting as a gigantic storage tank that has been filling up for eons. Another possibility points to a geological process we have not yet witnessed. Perhaps there are cryoval canals that spew out water and ammonia, but these could also be burying the ethane. As this slushy mixture erupts and freezes, it might trap ethane within newly formed ice layers, effectively sequestering it from the atmosphere and surface. Or could there be a more complex chemistry at play? Some laboratory experiments suggest that within Titan's unique conditions, ethane might be reacting with other compounds to form even more complex and heavier hydrocarbons, which then settle out as a kind of tarry sediment on the lake beds and plains. This would mean the ethane is being transformed, its signature lost in a more complex sludge. Each of these ideas has its own complications. A subsurface reservoir would have to be truly immense, and we have no direct evidence for its existence. Burial by ice would require constant, widespread geological activity, and the chemical conversion theory relies on processes we have not yet observed in action. The missing ethane forces us to confront the limits of our planetary models. It shows us that a world can follow the basic rules of chemistry and physics, yet still produce an outcome that completely defies our expectations. What other hidden processes are at work on this hazy moon, quietly balancing an equation we have only just begun to write? Two tiny moons perform a delicate gravitational ballet just beyond Saturn's main rings. Pandora and Prometheus are the shepherds of the F-ring, a narrow, contorted band of ice and dust. These small, irregularly shaped moons orbit on either side of this fragile strand, and their constant gravitational tugs are what keep it sharply defined. As Prometheus, the inner shepherd, swings close to the ring on its slightly faster orbit, its gravity pulls a stream of material inward, plucking a tendril of ice particles from the ring's core. This creates a deep channel and a temporary kink in the ring structure. Then, as Pandora, the outer shepherd, passes by, its own gravity tugs material outward, helping to push any stray particles back into line. This relentless back-and-forth influence prevents the ring from spreading out and dissipating, confining it to its narrow, brilliant path. The result is a constantly changing celestial artwork. The F-ring is not a smooth, uniform band. It is a dynamic tapestry of braids, kinks, and bright clumps that form and dissolve over days and weeks, a direct product of this gravitational shepherding. Yet this elegant system is fraught with peril. The orbits of Pandora and Prometheus are chaotic, their paths subtly shifting with each close encounter. They are locked in a gravitational resonance, a repetitive dance where their positions relative to each other and the ring change over time. The great mystery is how this chaotic dance does not tear the delicate F-ring apart. One miscalculation, one slightly closer approach from either moon, and their gravitational pull could shred the very structure they are meant to contain. How does this system maintain its fragile stability? It appears to be a self-correcting mechanism. The moon's gravity shapes the ring, but the ring's own collective gravity also exerts a tiny but significant pullback on the moon's, helping to stabilize their chaotic orbits. It is a delicate feedback loop, a cosmic balancing act that has persisted for millions of years. Why have these moons not collided or been ejected from their roles entirely? Their survival suggests that this chaotic dance is in fact a stable one, a complex gravitational arrangement that we are only beginning to model and understand. These two tiny shepherds, forever dancing on the edge of chaos, hold the key to one of Saturn's most intricate and beautiful structures. The same dark dust that paints one side of Iapetus may be a clue to an even deeper orbital mystery. This moon does not circle Saturn in a polite, flat plane like its major siblings. Instead, its path is wildly tilted, tracing a steeply inclined orbit that carries it far above and below the planet's equator. It is a cosmic maverick, a rebel swimming against the celestial current. Such a pronounced inclination is extremely unusual for a large moon, and it points directly to a chaotic and violent history. In the orderly disk of debris that typically forms around a planet, moons coalesce from material orbiting in a flat plane, inheriting that flat, aligned path. Iapetus, with its 17-degree tilt, clearly did not form this way, or if it did, something colossal knocked it off course. So what immense force could have grabbed this 900-mile wide world and thrown it onto such a skewed trajectory? The most dramatic explanation is a giant impact. A catastrophic collision with another sizable body early in the solar system's history could have literally punched Iapetus, sending it tumbling into its current steeply inclined orbit. This would have been an event of almost unimaginable violence, a blow powerful enough to rearrange the moon's very path around its primary. Yet such an impact would also be expected to shatter the moon, or at least leave a single colossal basin, evidence we do not see on its varied surface. Another, more subtle theory involves a gravitational dance, a close encounter with another large moon that has since vanished. In this scenario, a gravitational slingshot effect could have gradually, or perhaps suddenly, pulled Iapetus into its high inclination. This lost sibling might have been ejected from the Saturnian system entirely, cast into the darkness of interstellar space, leaving Iapetus as the sole evidence of their ancient gravitational tango. The problem is that both of these theories have their flaws. An impact violent enough to create this tilt might have also created a debris ring that we do not see. A gravitational encounter requires a very specific and unlikely set of initial conditions to result in a stable, high-inclination orbit like the one we observe today. This leaves us with a fundamental question about the early days of the Saturnian system. Was it a far more chaotic and crowded place than we ever imagined, a celestial shooting gallery where moons routinely collided or were flung away? Iapetus, with its strange orbit and its two-toned face, stands as a silent monument to that lost era of chaos, a puzzle whose solution is written in the empty spaces and gravitational echoes of a system we are only just beginning to understand. Deep beneath the layers of metallic hydrogen and churning clouds, the very heart of Saturn remains one of its most profound secrets. We cannot see this core, nor can we probe it directly. Everything we know is inferred from subtle gravitational tugs and complex magnetic fields, a celestial diagnosis based on whispers. The leading model, born from these measurements, suggests a central region of rock and ice, a compact sphere perhaps 15 to 18 times the mass of Earth, crushed under unimaginable pressure. This is the classical view of a layered planet, a dense seed around which the gaseous giant accumulated, but newer, more puzzling data challenges this simple picture. The planet's gravitational field is surprisingly smooth, lacking the sharp signature you would expect from a distinct, solid core neatly separated from the enveloping hydrogen. This has led to a radical alternative, the idea of a diffuse or fuzzy core. In this model, the heavier elements of rock and ice did not remain in a neat central lump. Instead, they may have been mixed and diluted over billions of years. stirred into the surrounding metallic hydrogen like chocolate syrup, swirled into a vast, dense milkshake. The core is not a single object, but a gradual gradient of increasing density and heavier elements, blurring the line between the planet's center and its outer layers. This raises a fundamental question about Saturn's entire history. Did it form with a solid core that then slowly eroded and mixed upward, or did it begin as a more homogeneous blend of gas and dust, with the heavier elements never fully settling out? The answer rewrites the story of how gas giants are born, and then there is the most fantastical possibility of all, a phenomenon that sounds like science fiction. At the immense pressures found in Saturn's deep interior, the carbon from methane molecules could be squeezed so intensely that it crystallizes, first into graphite and then into actual diamonds. These diamond hailstones, some potentially the size of icebergs, would then sink slowly through the liquid metallic hydrogen interior, a glittering rain falling for thousands of miles toward the hidden heart of the planet. Could Saturn's core be a repository of such cosmic gems? While the evidence is still circumstantial, the very possibility highlights the extreme and alien nature of the physics at play. Each model, from the rocky sea to the fuzzy gradient to the diamond shower, paints a different portrait of the giant's hidden center, a place we may never see but whose mysteries define everything we observe from the outside. While the North Pole's hexagon captures our attention with its stark geometry, Saturn's South Pole conceals a storm of equal intensity and mystery. Here, a colossal polar vortex rages, a hurricane-like maelstrom with a perfectly defined eye that has remained locked in place for decades. This is not a fleeting tempest but a permanent fixture, a whirlwind of clouds so vast its eye alone could swallow the entire Earth. The sheer scale is staggering, but it is the storm's unwavering stability that truly baffles scientists. On our own planet, hurricanes are fueled by warm ocean waters and dissipate quickly over land. Saturn has no ocean, no land, just an unbroken fluid atmosphere. So what powers this eternal storm, and why does it never wander from its polar throne? The vortex is thought to be a manifestation of Saturn's immense internal heat, rising and interacting with the planet's rapid rotation. As warm air from the deep interior surges upward at the pole, the Coriolis affect the same force that spins hurricanes on Earth, whirls it into a tight, furious vortex. The planet's own spin acts like a cosmic containment field, pinning the storm directly over the South Pole and preventing it from drifting into lower latitudes. This creates a self-sustaining atmospheric engine, a chimney of sorts where rising air is constantly organized into this persistent, rotating structure. The towering eye wall, a sheer cliff of clouds that plunges deep into the atmosphere, is a testament to the violent contrast between the calm, sinking air in the center and the raging winds that encircle it. But this explanation only deepens the puzzle of its longevity. Why has this vortex persisted, unchanged for so long, while other atmospheric features come and go? It suggests a profound and delicate balance in Saturn's global weather system, where the flow of energy from the planet's hot interior to the cold of space is channeled and focused directly at the poles. This stable polar vortex forces us to ask if it and the northern hexagon are two sides of the same coin, different expressions of the same fundamental planetary process. Are we seeing the signature of Saturn's hidden heart, beating out a rhythm that we can only perceive in these immense and permanent storms? Among Saturn's many rings, the faint and isolated G-ring seemed for decades to be a structure without a source. It is a delicate, ghostly band of dust, floating alone between the bright main rings and the powerful gravitational pull of the giant moon Mimas. For a long time, its existence was a puzzle. What could possibly maintain this tenuous ring so far from any obvious parent body? The answer arrived not with a grand discovery, but with the identification of a tiny, almost invisible speck. Hidden within the G-ring is a minuscule moon named Iapetus, a body so small it is barely more than a kilometer across. Its gravity is far too weak to hold onto a traditional ring, but it plays a different, more subtle role. Iapetus is the ring's secret heart, a source constantly feeding the void around it. Scientists believe this tiny moon is being pummeled by a steady rain of micrometeoroids. Each tiny impact blasts a puff of fine, icy dust off its fragile surface, a slow-motion erosion that continuously replenishes the ring's material. The gravitational influence of mimas orbiting nearby then acts like a cosmic shepherd, its regular tugs confining this freshly generated dust into the narrow, stable arc we observe. Yet this elegant explanation only deepens the central mystery. The G-ring is a delicate balance of creation and destruction. The same micro-impacts that create the dust also threaten to grind Aegeon down to nothing over millions of years. Why has this tiny moon not been completely pulverized after billions of years in such a violent environment? Is Aegeon itself a fragment of a larger, more ancient moon that met its end, and are we simply witnessing the final stages of its slow disintegration? Or is there a hidden process we cannot see, perhaps a reservoir of larger boulders within the ring that occasionally collide, creating new dust and even new moonlets in a continuous cycle of death and rebirth? This faint dusty ring and its tiny guardian present a profound question about persistence. How does such a fragile system endure in a solar system ruled by gravity and relentless bombardment? It is a whisper of a structure, a temporary sculpture of ice and dust, entirely dependent on the slow, silent erosion of a single kilometer-wide world. Even Saturn's serene, banded face is a mask that slowly transforms over time. The planet's iconic cloud belts and zones, those stripes of tan and gold, are not permanent features. They undergo dramatic shifts in color and intensity, a slow-motion chameleon act on a planetary scale. Observations stretching back over decades and even centuries show that these bands can darken, lighten, or change their hue entirely, sometimes over the course of a single Saturnian season. A pale, creamy band can deepen into a rich, coppery brown, while a dark belt can suddenly fade as if bleached by some cosmic sun. What colossal forces are repainting this gas giant? The primary suspect is the slow march of the seasons. Saturn's tilt is similar to Earth's, meaning its hemispheres experience decades-long summers and winters as it makes its 30-year journey around the sun. During a hemisphere's summer, the increased sunlight is thought to drive more powerful atmospheric circulation. This could stir up deeper layers of the atmosphere, bringing different chemical compounds up into the cloud tops. The bright upper clouds are believed to be made of ammonia ice, but deeper down, there may be layers of ammonium hydrosulfide or even water ice crystals. A change in season might alter the updrafts, pulling these different colored particles from the depths and changing the palette of the entire band. It is like a planetary scale art project, with sunlight dictating which colors rise to the surface. Yet seasons alone cannot explain the sudden, localized changes. Another theory points to powerful, sun-driven photochemistry. The intense ultraviolet light from the sun can break apart molecules like ammonia, allowing them to recombine into more complex compounds called tholins. These tholins are often a reddish-brown color, and they could be responsible for the darkening we see in certain belts. A third possibility involves the planet's own internal heat. Saturn radiates more than twice the energy it receives from the sun, and this immense internal furnace is constantly churning the atmosphere. This churning could create periodic upwellings of fresh, bright material that coats over darker regions, or it could expose darker layers from below. The changing colors are likely a complex conversation between all these factors, a dialogue between the external push of sunlight and the internal heat of the planet itself. We are left watching a world whose very complexion is a living document, a visible record of the invisible forces raging within and without. Even the dust that drifts through Saturn's domain tells a story of cosmic origins. During its long mission, the Cassini spacecraft performed an experiment of incredible subtlety, its instruments tuned to detect the faintest of impacts. It was listening for the ping of microscopic particles striking its surface, and amidst the expected haze of local dust, it found something extraordinary. A tiny population of grains stood out, not for their size, but for their speed and direction. These particles were moving far too fast and on trajectories that could not be explained by orbits within our own solar system. They were visitors from the void between the stars, minuscule pieces of other solar systems that had found their way to ours. This was not Saturn's dust, but the galaxy's. The significance of this discovery is immense. For the first time, we were able to capture and analyze the actual building blocks of the cosmos, material unaltered by the violent processes that formed our sun and planets. These interstellar grains are the pristine remnants of the galactic raw material from which all stars and worlds are forged. Their composition, rich in a specific mix of elements like magnesium, silicon, iron, and calcium, reveals a startling diversity. They are not all the same, suggesting they were born in different types of stellar explosions and forged in different cosmic environments before being cast adrift on the galactic winds. Finding this material at Saturn was a strategic triumph. The planet's position and the spacecraft's long duration provided a stable, long-term observatory far from the contaminating dust of the inner solar system. It gave us a clean window into the composition of the local interstellar cloud, the vast region of sparse gas and dust through which our solar system is currently drifting. Each of these hyper-fast dust motes is a tiny messenger carrying a chemical fingerprint of its birth star. What do these cosmic crumbs tell us about the galactic neighborhood we call home? They suggest it is a place of mixed heritage, where material from various stellar deaths has mingled over eons. This interstellar dust is the very seed from which new solar systems grow, and by studying it, we are essentially reading the recipe for worlds. We are learning what our own solar system was made from, and by extension, what other planetary systems across the galaxy might be made of as well. The ringed planet, it turns out, is not just a world of mysteries, but a gateway to the galaxy itself. From the faint whisper of interstellar dust to the roaring tempest at its poles, Saturn reveals itself not as a static jewel in the sky, but as a living, breathing, and profoundly mysterious world. We have journeyed through 25 of its deepest enigmas, from the geometric perfection of its north polar hexagon to the transient, ghostly spokes in its rings. We have witnessed the ring rain steadily erasing its most iconic feature and explored the methane seas of Titan, a world with a climate engine that defies logic. We have encountered the two-faced moon Iapetus, the cosmic sponge Hyperion, and the hidden ocean of Enceladus, a tiny world that shouts the potential for life into the void. We have grappled with Saturn's impossible hot atmosphere, its unmeasurable day, and the chaotic dance of its shepherd moons. We have pondered the fuzzy nature of its core, the seasonal shifts in its cloud belts, and the silent, enduring storms locked at its poles. Each mystery, from the great white spots to the missing ethane, from the propellers to the orbital swap of Janus and Epimetheus, is a thread in a tapestry of profound complexity. This is not a world that offers easy answers. It is a dynamic system of forces in delicate balance, a celestial laboratory where the fundamental laws of physics play out on a scale we are only beginning to comprehend. These puzzles are not dead ends. They are the very engines of discovery, pushing our technology, challenging our theories, and forcing us to look deeper and think bigger. They remind us that the universe is far stranger and more wonderful than we can often conceive, so we turn the question to you. Of all these enigmas, which one captures your imagination the most? Is it the hidden ocean of Enceladus and the tantalizing possibility of life, or the stark geometric perfection of the polar hexagon? What do you believe a future mission, sailing through those ethereal rings, might finally reveal about this Lord of the Rings? The conversation is just beginning, and the greatest discoveries at Saturn may still be waiting.